experiences with us.
So let us begin with our today's proceedings. To begin our day, it is our great privilege to be around one of the most motivating and technically advanced personalities amongst us. To introduce our second keynote speaker, Professor Ram Vilas Pachori sir, I would like to invite our Professor Thiagu Priyadarshan to give us a brief introduction of our keynote speaker.
A warm good morning to everyone present here. So it's my great honor and privilege to introduce our esteemed keynote speaker for this session, Professor Ram Vilas Pachori. Professor Pachori is an Institute Chair Professor and Professor HAG at the Indian Institute of Technology, Indore. He is a distinguished academician and researcher whose work has had a significant impact in the fields of signal processing, biomedical signal analysis, machine learning, artificial intelligence, and healthcare technologies. He is a fellow of the Institute of Electrical and Electronics Engineers IEEE and a fellow of Indian National Academy of Engineering INEE, two of the highest professional recognition awarded to engineers and researchers for their exceptional contributions. Throughout his illustrious career, Professor Pachori has published numerous high-impact research papers, guided many scholars, led several prestigious research projects, and actively contributed to the advancement of science and engineering through his innovative research and academic leadership. His dedication to excellence in teaching, research, and innovation has earned him widespread recognition both nationally and internationally, making him one of the leading experts in his fields. Today, we are truly privileged to have the opportunity to learn from his vast knowledge and experience. I am confident that his keynote address will inspire us with valuable insights and new perspectives. Welcome you, sir.
I would like to request Thiago sir to come forward and present the bouquet to our respected keynote speaker, Professor Ram Vilas Pachori sir, as a gesture of our warm welcome.
Sir. सर ऑन करना है उसे साइड में से
Thank you very much for nice introduction, and thank you for the opportunity to be here and to be part of this conference and to deliver this keynote speech. So there is actually in the literature or in the, like even in conference you'll find that there is a lot of discussion on machine learning, AI, data science. When you go for medical applications, then actually in issue of data science we also need science of data. So when we go for science of data, then there is a lot of use of signal processing. So in this talk, we will see use of signal processing and machine learning to design intelligent computing systems for healthcare applications. And in this talk, two such systems will be presented, and with the two major applications. One is for schizophrenia diagnosis, and second one for brain-computer interface. And both will be based on brain waves, electrons, pherogram signals. So there is also actually a need of understanding of signal processing. So in this talk, I will also explain you signal processing from the basics, and we'll go to the advanced, and then whatever currently there is a focus of signal processing that will be presented, and then we will see those two applications. And there is a lot of interest of combining signal processing, machine learning together to develop intelligent systems. And such intelligent systems can be used to detect the disease in the initial stage in rural areas, and also in urban areas we have less number of doctors, more number of patients. So such kind of systems can be useful to perform efficient diagnosis by the doctors in urban areas. So everywhere there are various applications, there is a lot of use of such kind of system. So with this background, let us start this talk. First we will see transform, then Fourier transform, short time Fourier transform, wavelet transform, continuous wavelet transform will be explained. Then we will see this 1998. Actually, this new signal processing direction has come, that adaptive signal processing, and that why Wang and others they have proposed empirical mode decomposition. So that will be explained. Then this adaptive signal processing decomposition based multi-channel signal processing will be explained, and then we will see empirical mode decomposition, then iterative filtering, and then our group has proposed multivariate iterative filtering, and then based on that we have developed two intelligent computing systems that will be presented, and we will see two major applications. One is for detection of schizophrenia, second one is for motor imagery based brain computing tools. And in the end, conclusion will be provided. So this like everywhere these days, everybody talking AML. No? This is common. Even school kids also talk about AML. This is so. Similarly, transforms are also very common. Like whenever you see data, that is also one kind of signal. So wherever you have signals, then transforms are there. So transforms are everywhere, like machine learning, and signals contain a lot of information. And to understand the information, we actually go in another domain, and then we transform, and we understand that information, and by doing that processing, we come back in again in actual domain. So transform is like a bridge between two domains, time domain and other domain, maybe frequency domain, for example. So we do this lot of processing in this frequency domain, and there are certain advantages. And by doing that, actually we come back. So these frequency domain that also can be used as a features, can be used. It is more robust to noise. So there are many reasons for that. So there is a lot of interest going in transform domain. And first transform was proposed by the Joseph Fourier in 1807, and Joseph Fourier was actually working on the prism. He was from physics background, and he observed that white light can be decomposed into 7 colors. Then he got idea white light can be decomposed into 7 colors. Then why we cannot decompose this complicated signal in terms of simple functions? And then he represented a complicated signal in terms of sinusoidal functions. So there are two operations. One is analysis, and second one is synthesis in the Fourier transform. So analysis, actually what we do, we integrate signal from minus infinite to plus infinite. So we get the frequency domain, there is no time in the frequency domain. Synthesis, we integrate frequency from minus infinite to plus infinite. So there is no frequency in the time domain. So time domain and frequency domain both are mutually exclusive. So when you are in time domain, there is no frequency domain. When you are in frequency domain, there is no time domain. So there are many types of signals, but one of the major classification of the signals is stationary and non-stationary signals. So we use mathematical models to represent the signals. If any of the parameter is changing with respect to time, then we call them non-stationary signal. So here you can see the two signals. One is stationary signal, second one non-stationary signal. And if you apply Fourier transform, then actually both are giving same spectrum. So that is one of the major limitation of the Fourier transform, because you are getting same spectrum for stationary signal and non-stationary signal. So motivated by that limitation, there has been a new direction in the signal processing, that is actually which will give you unique spectrum representation for both signals. Like for stationary signal you should have different spectrum, and non-stationary signal you should have different spectrum. So then this new direction of signal processing started, that is known as time frequency analysis, like where both domains are together, time domain and frequency domain, so that you can have time varying frequency representation. So in case of stationary, frequency will be constant, and non-stationary it will be varying with time. So this time frequency analysis, the first method that was proposed in the literature, that was short time Fourier transform. So what actually we do, we non-stationary signals, in real life signals are non-stationary, most of the signals, because change is the rule of life. In this world, nothing is permanent except change. So wherever there is change, there is a non-stationary. So you will find non-stationary everywhere in the nature. And the short time Fourier transform, what we do, we divide signal to different segments, and we assume that each segment signal is stationary. Then we apply Fourier transform, and arrangement of Fourier transform gives us short time Fourier transform. So in short time Fourier transform, this is complex quantity. So for representation purpose, we can experiment with the STFP, that is known as spectrogram. And Geber says if you use a Gaussian window, then this is the optimum form of the short time. So that we call Geber transform. In short time Fourier transform, the spectrogram, just here you can see two examples. When you have speech signal, when you speak in MATLAB, it looks like this, and this is linear chip signal. And there are two spectrograms based on the selection of the window. So like this, you have a wide analysis window that gives you narrow band spectrum, so it has good frequency resolution, poor time resolution, and wideband spectrogram, it has poor frequency resolution, good time resolution. Similarly, here also you can see it. So it depends on the application. If you want a good frequency resolution, then go for narrowband spectrogram, and if you want a good time resolution, go for wideband spectrogram. There is no thumb rule. So in short time Fourier transform, we don't know how to select size and type of the window. This is the actually this is based on the trial and error or based on the experience. And there are many windows, and like Hamming, Kaiser, Rectangular, Gaussian window. And this resolution, time resolution and frequency resolution, both are actually associated, both are governed by the Heisenberg identity principle. So it is not in our hand, it is based on this principle. So if you have good time resolution, forcefully you will have poor time, poor frequency resolution. That is actually inherent to the nature. So in short time Fourier transform, suppose you have low frequency component, then we need analysis window that is actually wide in time domain, and if you have high frequency components, your window should be narrow enough in time domain. So that flexibility is not there in the short time Fourier transform. Then actually because once you have selected window, then its type and size is fixed for entire analysis. So so this short time Fourier transform actually gives you fixed frequency resolution in both domain, time domain, frequency domain. So when your signal has different kind of frequency components, we need actually multi-resolution analysis. So low frequency. So then this limitation of the STFP actually inspired in the literature to develop wavelet transform. So here actually we use scale concept, and the scale it depends on the type of frequency component. So if you have low frequency component, then you will use large scale that will give you poor time resolution and better frequency resolution. And if you have high frequency component, then we use low scale. It gives you good time resolution, poor frequency. So we known as multi-resolution analysis. So when you go to restaurant, then actually there are many spoons are available. It depends on the type of food. So if you want to have noodles, then use for, because your food is discontinuous, spool is also discontinuous. So discontinuous spool can be nicely handled by the discontinuous spool. So similarly, different kind of frequency components, you have different scales. So that is actually that flexibility is there in the wavelet transform to use various scales for different frequency components present in a signal. So this is mathematical expression for continuous wavelet transform, and actually the signal that you want to analyze I the mother wavelet, and while doing this expression, you have left hand side continuous wavelet transform, this function of tau and scale, shifting per scale, and this also similar to short time Fourier transform that we square magnitude of the STFT gives a spectrogram. Similarly, here square magnitude of the continuous wavelet transform gives you scale. So that is actually, and the scale is inversely proportional to frequency. So this continuous wavelet transform gives you scalogram, and scalogram can be converted into time frequency representation. So you also can get time frequency representation using scalogram. So here good thing is that now you have low scale. Low scale gives you good time resolution that is suitable for high frequency components, and your large scale that gives you poor time resolution and suitable for low frequency components. So all kind of frequency components can be analyzed with the desired resolution. So here this is just an example speech. I think here it is working nicely. Maybe here it is not in the range. So here this is the speech signal that actually MATLAB, and these are the two scalograms, the wavelet bump and Morse. So this actually this representation has brought an interesting direction in the machine learning AI/ML, and that is actually like in issue of signal, we need data in the form of images. So like convolutional neural network, deep learning kind of approaches. This now issue of the signal, this image representation can be given as an input. So this opens a new door of machine learning where image-based classification can be done for the one-dimensional signal. So time frequency analysis gives you an opportunity where one-dimensional data can be represented by two-dimensional images, and they can be used as input to convolutional neural network or deep learning or advanced machine learning to classify the data in the form of images. So till now, signal processing, that actually whatever you have seen, Fourier transform, short time Fourier transform, wavelet transform, the basis functions we are designing from our side. So firstly, we are representing signals in terms of the basis functions. So real life signals are not sinusoidal like electroencephalogram, electrocardiogram signals. They are not sinusoidal. They are not wavelet. But forcefully we are representing these real life signals in terms of functions we design from our side, because that is man-made functions. So we understand real life signals in terms of man-made functions. 1998, this new direction of research has come, that is by Wang and others. That is known as empirical mode decomposition. There actually you don't need to design basis functions from your side. On the other hand, these basis functions will be obtained from the signal itself. That is why we call them intrinsic mode functions. So at this point of time in the signal processing, there are two directions. One is fixed basis based approach. Second one is adaptive basis function based approach. Fixed basis functions like Fourier transform, wavelet transform, etc., where we design basis functions from our side. Adaptive basis function, you don't need to design basis functions, and they will be obtained from a signal itself, like empirical mode decomposition, empirical wavelet transform, adaptive filtering, etc. So actually, this is one point in signal processing. Other point is also that is number of channels. So in real life, there are many scenarios where we have multi-channel data, and some of the examples are here. So the first one is here for diagnosis. We record actually for 2-3 channels vibration data, and this is electroencephalogram EEG signal recording, where we record brain waves, brain signals with the multiple electrodes in the cap, and the ECG electrocardiogram signal recording, we use number of leads to record multi-channel ECG data. In all cases, whatever data you record, they are multi-channel in nature, and if you analyze this multi-channel data individually, then actually we are losing the correlation between the channels and mutual information we are not considering. So in order to preserve mutual information and correlation between the channels, there is a use of multi-channel signal processing in the literature. And also, if you use this adaptive signal processing concept, adaptive basis function based approach, then each channel will give you different number of components because this is data dependent. So each channel, for health applications, if you use adaptive signal decomposition techniques, for one channel you can get 8 components, other channel you can get 5 components. So how to compare 5 with 8? That is actually a problematic issue. So in order to have same number of components by all channels, it is actually necessary to use multi-channel signal processing or multivariate signal processing. So due to that, now there is new direction of signal processing actually coming in the literature. That is development of intelligent systems based on multi-channel signal processing machine learning approaches. So that is actually intelligent computational systems. That actually use signal processing and machine learning both together, but signal processing for multi-channel control. So this it was just started in 1998. The empirical mode decomposition. Here you don't need to design any basis functions. You can apply this method for any data. You don't need to assume any conditions. So you have data, and then you determine extremas, maximum minima, then interpolate them, then we do envelopes, upper envelope, lower envelope, and then we subtract average of that from the signal, then we get the residual. And residual should satisfy two basic conditions of IMF, intrinsic mode function. First is number of extrema and number of zero crossing should be differ at most by 1. So this condition ensures that whatever IMF you have, it looks like sine cosine function. And second condition ensure that average value of the residual is 0. So this condition makes sure that whatever IMF you are obtaining, that is symmetric in nature. So by combining these two conditions, we get such IMFs which are symmetric in nature or look like sine cosine function. So based on this observation, these IMFs have been represented using amplitude and frequency modulated sinusoids. So once you have first IMF, then actually we subtract from the signal, get the residual, and then repeat this process. So in that way we get all possible IMFs from the data. And here you can see this is the first IMF and this is the last IMF. First IMF represent the lowest scale or highest frequencies. So this is known as the details. And last IMF that represent the largest scale and lowest frequency, that is approximation. So Professor Patrick Flandin and his team, they have shown that these components, whatever you get IMF, they are similar to wavelet decomposition. But good thing is that here you don't need to design wavelet and you don't need to know number of labels for the decomposition. So it is automated in nature like machine learning kind of thing. So based on this concept, various methods have been proposed in the literature for multivariate signal analysis. Complex EMD, rotation invariant complex EMD, bivariate EMD, multivariate EMD, fast EMD, etc. And empirical mode decomposition has two major limitations. One is mode mixing and lack of mathematical theory. So that motivated actually a lot of signal processing since its development 1998. After that, so many people, so many approaches being developed in the literature. But in signal processing, approaches are not like machine learning, is like very few, but they're standard approaches. So one of such approach is iterative filtering, and here actually in this talk, our focus will be on iterative filtering and multivariate filtering, how they can be used for computational systems. So iterative filtering here, it has mathematical theory, and it gives you similar kind of approach for decomposing data, like what EMD do automatically. So based on the extremas, we design the filter length and cutoff frequencies, and design filter is used here, and then we subtract from the signal, then we have residual, and this we do in reasonable number of times, then this becomes IMF. So we call it first IMF. Then for next process, first IMF is subtracted from the data, Then we get new residual, and the residual we repeat the same like EMD and then get the all IMs. This is just one example how it works. So here you can see this signal has three IMFs, and this is the filter designed. So if you the filtered signal, subtract this filtered signal from here, your first IMF, subtract from here the residual, then design the filter, the filtered signals, you subtract filtered signal from here, then you have second IMF, first IMF, second IMF, subtract from here, then you have new residual, and there is no filtering, so residual will become third IMF. So that is the very simple concept. Now this is for univariate single channel. Now for multi-channel, this is the simple approach. So you have signal, then find the number of extremas, then design the filter. Filtered signal is subject to a signal, then residual, and then we satisfy two basic conditions, that's stopping criteria to stop the process. The first one is standard deviation is nearly zero. This means signal is nearly now slow. It is weak, so we can stop it. And the stopping criteria, number of extrema less than 3. So this means signal doesn't have oscillatory behavior. So you don't need to dampen, no frequency, no need to compress. So you can stop it in the middle whenever you satisfy this one of the conditions. And once first IMF is obtained, then we go for another one like that. So we repeat the process. Now, if you apply this concept for multi-channel signal processing, multi-channel data, then each channel will have different number of extremas, different number of cutoff frequency, different filters. So number of IMS will be different for each. So what we suggested, you take the actually all extremas you find from the all channels, and then take maximum value of that extrema and use this as a common for all channels. And that based on this extrema, you design the filter, and that filter will be used for all channels. And in that way, each channel will give you same number of IMs. So mode alignment property will be preserved. So this is just one example how it works. So you have two channel data. In first channel there are two IMF, second channel there is one IMF. So if you individually apply, then first channel will give you two IMF, second channel will give you one IMF. So there is no mode alignment property. Both channel has different number of modes. So we have selected best maximum value of the filter, maximum filter. So that filter, this one, actually this is the maximum cutoff frequency, that will be common for both. And then you actually subtract this from this, then your first IMF. So this is the two channel IMF. First IMF, then subtract from here, then you have residual. This again design filter, take the maximum value here and subtract. So like that. So you have first IMF, second IMF, third IMF. Actually, two channel IMFs. Now we will see its application for electroencephalogram EEG signal. So this is a human brain. It has four lobes: temporal lobe, frontal lobe, parietal lobe, occipital lobe, and we use EEG cap. This is a 10 to 20 system, and these electrodes are arranged in such a way that actually they cover all lobes. So just for an example, this is the obtained two channel EEG data, and then this but depends on the number of channels. You have 256 channels, then will be 256 EEG. And now we will see it's two applications: schizophrenia detection and motor imagery brain computer. So schizophrenia actually just briefly there's one it's one of the serious neurological disorder. It's like all disorder what we know, that is one movie, A Beautiful Mind, in 2001. It is based on the Professor John Ness' life. He got Nobel Prize in Chemistry. So Professor John Ness, he was a student at Princeton University. There was a roommate, his name was Charles, but there was no Charles at all in the university. So that actually you make such people your friends, they don't exist in life. So the imaginary people, they become real for you. And later, this Charles introduced his niece to Professor John Ness, and when Professor John Ness actually he did excellent work in his undergraduate time, and then he got placement in MIT. MIT, when he was teaching the class, there was one person, William and his team. They used to take help from the Professor Jones to report the course. Those days, course used to publish in newspapers. And this Professor Jones, actually, they took him from the class, and after 2 hours, they found that this initial William, the neurologist sitting in front of him, and neurologist saying you are suffering from schizophrenia. So these three persons, Charles Nice, and William, all were imaginary people. They were not existing, but for Professor Jones, they look like real people. And later, actually, his wife used to tell that the neurologist is saying that you are suffering from schizophrenia. And so his wife is saying these three persons are imaginary people. And these actually three persons used to convince him that your wife is telling that. So the person is always between actually two kind of people. Real people and imaginary people. Very complicated. And later he got novel. Actually, when he lost his job due to schizophrenia disease, and he used to teach in he used to audit classes in Princeton University, in Canberra. And once one person is coming and asking where is the Professor Jonas, then he met Jonas and he said, "We are nominating you for Nobel Prize." And he was nominated, and he got Nobel Prize. So that once he got Nobel Prize, then he was delivering his speech, and he is acknowledging his wife. Then three persons, imaginary persons, are also standing there. They also want actually that Professor Jonas should acknowledge these three people. So this is the situation. That is very complicated. And later, actually, he was mathematician. He himself understood that he has disease because this Charles niece and she was looking always similar. Many years are over, and she is always in the same dress. She is not aging. Then she says, "This is not. This is, it cannot happen in real life. It is a disease." When he understood himself. So this is actually schizophrenia is a very serious disease, and it affects around 20 million people worldwide. It's 1% of world population, more than 1 million people in India. So there are hallucinations, and hallucinations like you see such things which are not there, you listen such things which are not existing. So very different type of disease. And if you can detect this initial stage, then a very treatment, it can be controlled. So this is our proposed system for this diagnosis of schizophrenia. We have multi-channel data, then through segment, pre-processing, multi-channel data filtering that we have proposed. Then it will give you n modes for each channel, same number. Then for maybe the first time we have separated rhythms, they are also multi-channel in nature. Then we extract set of features from these multi-channel rhythms, and then we use for this classification purpose, and that gives you automated classification of schizophrenia. For the study purpose, we have taken this publicly available database from Poland, and it has schizophrenia case 14%, DLD case 14, and both have 7 months, 7 years. 19 electrodes are used for the recording of the data, and sampling rate is 250 hours, duration is 15 minutes. So here now you can see this is 3-channel data. And these are the options second, third, fourth multivariate intensity parameters. And from the forest spectral density, you can see they are actually multi-channel. They are like mode alignment properties present. So what is doing? It is bringing same frequency component from the all channels. That is the beauty of the multi-channel synchronous. Then this rhythms actually EEG had very interesting story. In brain waves, this is developed by invented by the Burger. And Burger was actually horse rider in German army. So when he was fighting for a battle, and he fell down from the horse. His sister, she was many kilometers away from that place, and sister came to know that her brother has got lot of injuries. Fell down from the horse. And then she conveyed this information to parents, and parents sent telegram when Burger confirmed the same. So Burger believed that his brain was transmitting signals, and the sister brain was acting as a receiver to receive these signals. And after retirement of German army, he started doing research on this concept, and he invented EEG. electroencephalogram. And later he says whatever he was thinking that was not correct. But a good thing that he came. So that actually whatever Burger defined that was like rhythms that were based on the frequency spectrum. So once you have power spectral density like frequency spectrum, then all rhythms are there. So we have defined the rhythms in terms of multi-channel for the first time, and they are also dynamic based on the non-stationary concept. So now delta, theta, alpha, beta, gamma rhythm, they are multi-channel in nature, and based on the mean frequency coming in this range, then we take that IMF to make part of the summation. So in that way, we have actually segregated all IMFs into these 5 classes, and then delta, theta, alpha, beta, gamma rhythms. So adult parameter, they are commonly used in this brain computer interface applications. So we have for the first time we have used for this schizophrenia diagnosis. And when you apply these features to its say number of channels, easy rhythms, parameters, they are 285. So these features should not be used. Parsimony principle should be satisfied. So we have applied probability value based student test, and based on the probability value, we have actually we have ranked them, and the best 30 features have been selected out of 285, and you can see these box plots. They are statistically significant, but they are not well separable. So in order to make separable, improve the classification accuracy, we have used the machine learning based classifiers. So support vector machine, support vector quadrature, linear discriminant neighborhood recently classifiers, and then to measure the performance, we will accuracy, sensitivity, specificity, positivity, and ROC curve. Here you can see the performance of the proposed system in terms of accuracy, sensitivity, specificity, positivity, and ROC curve. And tenfold cross validation that actually gives you better performance, and with SDMPB classifier. And then actually we have compared our proposed method with other existing methods in the literature. So you can see that our proposed method gives better performance than the other existing methods in terms of all comprehensive parameters. The next application is motor imaginary brain-computer interface. That is actually a very interesting area, and it has a lot of applications. And sometimes you are not able to connect directly with the real world due to disability, like or for example, like you don't have like hand. So this robot hand can be designed, and then when we use brain waves to control that robot hand. So that is actually a concept of brain computer interface. So here you can see this is like a device, a robot head, artificial hand, and that can be controlled by brain waves. Brain waves we record EEG signals, then they go to computer or machines, and then actually machines will give you instructions or commands to this robot hand, so that you can control, you can connect with the real life. That is good brain computer. So it has many interesting applications: medical, environment, marketing and advertisement, education, self-regulation, games, entertainment, security, authentication. Mainly, there are 3 types of BCIs. One is based on the speech, like you are not able to speak, you just imagine, and then based on imagination, EEG signals are recorded and we decode what you want to speak. That is Stephen Hawking's case. And the second one is based on the visual cognition. So like whatever object I see, I can record EEG signals for that. And suppose I am not seeing, I am just imagining that object, then EEG signals also look similar to that. So those EEG signals can be used to decode that object, what you want to see. The third one is this motor imaginary. So like you are not able to, you don't have hand, but you can imagine up, down, left, right movement, and based on that imagination, EEG signals are recorded. So they can be used to control the artificial hand to connect with the real. So such kind of actually work we will see in this part. So we have used 2 databases. BCI competition for 2001, which has 9 subjects and 70 trials have been recorded. They were imaging left hand, right hand, both feet and thumb movements. And each data has been recorded 22 different positions. So you can see this is a BCI paradigm and this is a electrode configuration which is used for recording that. Second database, this database 2, each data has been recorded from 3 different subjects for imaging of left hand, right hand, both feet and tongue movements. And this is BCA paradigm, this is a electrode configuration. So this is our proposed approach for motor imagery and computer interface approach. So you have multi-channel EEG data and then pre-processing done, and this is our proposed signal processing approach, that is multivariate data filtering. Then you have common spatial pattern based on the features, and we do ranking and then the classification. So based on this, we have selected 4 IMFs. So this you can see the multi-channel IMFs for this 3-channel EEG data. And then just to use the results, calculation accuracy of the proposed method on BCI 42 data. So this there are 2 kind of scenarios. One kind of scenario we do subject dependent, other one subject independent. Both have their own applications. So this is subject independent, this is subject dependent. So subject variant, subject like this subject invariant, subject variant, subject dependent. So each subject you have accuracy number of features. This is for left versus right hand versus feet, left hand versus tongue, right hand versus feet, right hand versus tongue, feet versus tongue. So all these 2 class classifications, you can see the performance for subject dependent and subject independent. This is average instant recognition. And the second database that is for 3 subjects. This is for subject dependent case. This is subject independent case. So accuracy for left hand versus right hand, left hand versus feet, left hand versus tongue, right hand versus feet, and right hand versus tongue, and feet versus tongue. So all cases with number of features and the classification. Brain signals are highly variable, and you can see that number of feature selection is very important part, and the accuracy can change. So that is very important. And then we have compared our method with other existing methods in the literature. So you can see for the subject dependent case, there are various methods in our proposed approach. And then we have compared its MIF CSP with other existing methods that we have for this classification purpose. Then you can see out of this 5 classification problem, 3 classification problem our method is giving better performance, others is giving comparable. So we believe that our proposed method is actually a very important tool for BCI applications. And then why we have selected 4 IMFs, that you can see based on topology graphs and based on the feature representation. Once you go beyond 4, then actually these features are not separable. So that is due to separability, we have selected this number of 4 IMFs. There are other approaches also in the literature: variational mode decomposition, empirical mode decomposition, multivariate case. And we have compared multivariate data filtering with these multivariate DMT and multivariate EMT, and we found our proposed approach is better than these other 2 existing methods in the literature in terms of accuracy. So this is the conclusion of this entire talk. We have proposed schizophrenia detection method based on multivariate data filtering, and which has shown better performance than the existing methods in the literature. And we have also proposed multivariate data filtering based decomposition approach and based rhythm separation. That is conceptually different than the existing approaches for rhythm. And rhythm is the basic part of EEG processing. So these methods, whatever I presented, they can be explored for various applications where EEG signals and EEG rhythms are important parts. And whatever actually the rhythms in the literature you see, they are based on the prefixed basis functions, fixed frequency time. But our case, whatever rhythms are there, they are dynamic in nature. And we have seen that we have studied on 2 databases, multivariate filtering based approach for brain computer interface concept, and it's also better than other methods. And so the superior accuracy provided by CFC, MIF CSP algorithm proved that a promising candidate for MIBC. So this talk is based on this two of our recent studies. So I request all of you, in order to have more information about this presented work, please go through these qualifications. So please feel free to ask if you have any questions related to this topic. That's why I thought I finished in time, so that you will have time for questions.
Composition part. So I have taken one controller for the working manipulator. How can I select that manipulator with a flexible? So it is
The brain actually, brain waves can control. Like this, whatever the EEG, VCI, we have electrical spectrograms in the brain waves. Now brain waves are there always. They can control outside.
by the working manipulator, if it is voltage, it's a little bit higher, sir. But we control that voltage with the controller from brain signal. How
Yeah.
can we
Yeah. So like one is, for example, switch is there, electrical switch. This electrical switch, mechanical switch. Similarly, the switch also can be controlled by the brain waves. So like on off. So if you close your eyes, open your eyes, that based on that people have designed switch. So you have to actually find out whatever like voltage or whatever states you want to have from the E. Like based on the study, you can come up with the states of the brain waves, which can be used to control the manipulator. Yeah, can be. But brain waves are highly variable. There's a lot of variability. Based on one research, around 8,000 to 60,000 thoughts are there in a day, in the brain. So average person, they very slow brain, they have around 8 to 10, around 10, 12,000 thoughts in a day, and it goes up to 60. So now you can think what is happening in the brain. Brain is actually very powerful, and whatever people say is this, this. But once you grow in life, you after certain age, you will say everything is right. The thinking process is everything. By thinking process, you are the great person. By thinking process, you are the lower person. Everything, whatever your life, it is based on your ideas, thoughts. So it depends on the whatever thought you have mind, you become like that. So like thought is very important. Brain is actually whatever you do directly, indirectly, everything has connection with the brain. That is why EEG signal has information for all diseases, all activities, whatever you do. This whole time people used to read the brains, read brain waves, they used to read the dreams. Mandodari predicted in the dreams the driver is going to die after 2 months. So that is it. So dreams also like night when we sleep there are six indications. Awake, non-rapid eye movement, S1, S2, S3, S4, and last one rapid eye movement. So rapid eye movement is like Brahma Muhurta in India, 3 o'clock to 5 o'clock. So if you have seen in villages dreams in around 12 o'clock, they don't take seriously. But if you have seen dream in the morning time, then they will take seriously. And this may be interpretable. That may have importance. So a lot of people are doing research on understanding things. Fourier story was very interesting. I also wanted to tell Fourier story, but since I thought you will ask a question, so I summarize every question. Fourier actually was from France, and his father was tailor by profession, not mathematician. And when he was 4 years old, his parents died. And he used to work in hostel. In old time, there was no electricity like today we have. Students used to use candles for study purpose. And the remaining part of the candles, they used to throw outside. In Fourier, used to collect these small pieces of the candles and used to make a big candle when everybody is sleeping in the night. Fourier used to stay. And Fourier was actually not from noble birth, like in France. If you know your parents' information, then you are considered noble birth, and if you don't have information about the parent, then they don't consider. Fourier was in that category, that one. And society not allowing to go to school, was destined by religion. Then most of the actually study has done himself, and he was physically strong, and then he joined French army. And then French army, he got an opportunity to go to Ecole Polytechnic. And Ecole Polytechnic in Paris, where he was working on the prism. And he decomposed this white light to several colors, then he got idea. This color, white light can be decomposed to several colors, then why we cannot decompose this complicated signal in terms of simple functions? And then he developed Fourier transform. Same Fourier, he became founding director of Ecole Polytechnic, and later he was appointed scientific advisor of Napoleon. When people asked him earlier, you were son of Taylor, now you are scientific advisor of Napoleon, how do you feel? Then Fourier says, I am saying Fourier, this is just a matter of time. So Fourier understood time in such a manner that he represented complicated signal in terms of simple functions which are periodic with respect to time. So there are two things are very, very important. One is time and second one is thinking. The two, time is actually this signal processing. There are three independent forces: time, frequency, scale. Whatever is happening in this world, it has connection with time. Two persons are talking on phone. I don't know what they are talking, but I can guarantee you that they are talking about time. We are always talking about time. Time is always there. Time in this world, most powerful thing is time. Person is poor. He is not poor. He is poor due to time. He is rich. He is not rich. He is rich due to time. Time is actually inherent everywhere. Whatever you see, it depends on the scale. That is scale. Whatever you listen, it depends on the frequency. So the three independent forces matters.
Sir, I'm from Mechanical Batchman Engineering. What should I study to develop a machine or do research in technology sector?
It's a very good question. Actually, this please, but please sit down. There is a what actually happening. People are thinking that if you have like implemented something, you come up with the hardware, machine, that research. Research is actually innovation. Innovation, it can be in any way. It can be by algorithm also. It can be by hardware also. It can be by concept also. It can be by mathematical formula. So innovation actually can be from any way you can contribute to literature. What actually somehow people are thinking that this you are making device. This is like research. Research actually can be in any way. It is like an innovation. It is the kind of concept that is actually thinking. So now, what you should like for research, what you should study. So if you see, just I will give one example. If we were in Treta Yuga, that time good people used to stay nearby Ayodhya, and bad people used to stay nearby Lanka. So there was clear-cut separation between good people and bad people. If you want to become good to bad, bad to good, then you have to cross the white sea. Entire Ayodhya, there was only one bad person. Her name was
Okay.
Mantra. In entire Lanka, there was only one good person. His name was Vibhisana, and only very minor. And all they were separated like dweeps. When we came to Dwapar Yoga, then these good people and bad people they become part of one family, like Kauravas and Pandavas. Kauravas were set of bad people, Pandavas were set of good people, and the separation was reduced. When we came in Kali Yuga, then it has come in one person. Sometimes he is good, sometimes he is bad. One time he was nice person, now he is not nice person like that. Same thing is happening in the technology. Sometimes it looks like electrical engineering, sometimes it looks like mechanical engineering, sometimes it looks like computer science. So like car, our time when I did my engineering 2001, then we used to believe that car is mechanical system. Mechanical engineering people used to study car. But these days car has all areas of research. Car has electrical engineering, electrical vehicle, car has music systems, car has speech recognition, car has machine learning, car has computer science. Lot of automation is there in the car. So all areas are actually coming in the car itself. So it is one kind of interdisciplinary. So now these days actually research is a little bit challenging. Earlier you have to know only electrical engineering, computer science, mechanical. These days you should know many disciplines. So it is little bit like more studies needed. One should not focus on like you are from computer science. Computer science now you should also study other domains. So we should now actually learn as many as possible to survive. This our time is different. Other earlier research was different. So there are only two ways to do research at this point of time. Either you learn many skills, or otherwise you work in a team which has lot of skills. So in India, sometimes we are poor in working team. We are better in working individuals. So we should learn how to work in team. So we should actually learn from each other, and we should work in the team. Because when you start working on real life problem, then this narrow knowledge, narrow band knowledge, like one discipline is not sufficient. You have to go for disciplines. Like one example, Princeton University, like one university, Princeton, some other university in USA, they have made snake robot. Snake robot. Now you will find many of your friends, they don't know what is snake. They have not seen a snake also. Because snake will not come in the flats. If somebody, your friend is from forest, he will know so many things about the snake. In my village, many people, they will tell you variety of snakes. And they know various features of the snakes because they have seen closely. So sometimes when you work on real life problems, then other kind of knowledge that is not taught in the universities and classes, that is also useful. So outside of the classes, outside interaction, the outside things are also useful. Like the snake robot, snake, no teacher will bring snake in the class. This is the snake, these are teachers. So some many things we learn from outside that are also useful in here. So research actually we should learn always, and we don't know when it will be useful. Just I will give one example. In Treta Yoga, when Hanumanji was going to Lanka, there was one demonic, her name was Singika. Singika used to detect person based on the shadow image. And the shadow image was she used to use as a feature to identify whether this person belongs to Lanka or not. So if that person belongs to Lanka, then she used to welcome. Otherwise, she used to make that person as a fool. Today that we call biometrics. Instead of shadow image, we are taking image in metal of that thumb impression. Yes. So concept is same. When you bring it together. So, like if you talk to people like like you are doing agriculture, many farmers can give you a lot of ideas. You are doing in healthcare, where can give you so many ideas. Elderly people can give you a lot of ideas. So that is actually experience is very very important. We should also learn how to learn from the elderly people, experienced people. जहाँ न पहुंचे रवि वहां पर पहुंचे कभी और उससे भी बड़ा अनुभवी So experience is important. Elderly people, they have actually spent a lot of time in life. They have a lot of experience. They can share many ideas with you. So we don't know which idea is useful. So we should always actually keep learning. Learning is the attribute of human. But what we are doing now, we are not learning. We want machine to learn. Then it's problem. Learning is attribute of human. It is not attribute of machine. Machine is working under your control. Machine learning. Learning means it is continuous process. It will always learn. It is not learned. And once it is learned, then we use the system. So machine learning is always actually learning. You change the rule of life every time. But people are believing machine learning is a vector, it is magic. But many places it is useful. But if you connect machine learning with the health, human, then so many issues. So one of the major area that you will see, like for me, machine learning is not future. Mostly IoT is not future. But for me, I consider human machine system as the future. Maybe after certain years, you will find you are sitting, machines are also sitting with you. Now, how to interface with the machines? That is it. You are a nice person. I can talk to you nicely. But machine doesn't know whether you are a nice person or not. Machines are machines. So now many issues will come when machines and human both will be together. So like in Germany, you see the government has granted but the autonomous cars are coming, driverless cars are coming. And some cars are with drivers. Now all are human drivers. It is to control. It is to communicate. Now some cars driver will be no drivers. In some cars there will be driver. So it is a very so many issues will come. So maybe in future you have to enter such kind of. So you now you should learn such kind of skills where such kind of situations will be handled, will be solved. So that's different time, different kind of issues will come, problems will come.
Sir,
And reverse technology exists that we put the information to brain using signals and
It's very good question. So this is brain computer interfacing, computer to brain. So we give stimulus. Even it's in memory implantation, people that making neurons, actually, they are different regions. Opposite is also people are doing that is also one of the area of research. We want to make your brain active with the help of computational methods, implantation. That people are making biochip. These four lobes I have shown, and one lobe is not efficient, not active. Then you can put a chip, biochip, so that region will be active. Whatever any place you see, whatever like they're mapping here. So all neurons, sometimes some regions are not active. So people put chip to make that region active. That is actually very interesting areas where very less no work in that people are doing. And Western people do that.
sir,
There are two types of Babas in India. One is Petka Baba, second one is Chapetka Baba. Petka Baba means by birth that person wants to know about the God, Lord, always motivated for that. Chapet means he tried many things, now nobody worked, then he became Baba. So similarly, we need such kind of researchers of your age. They are childhood, they are actually motivated for this. That is it. So just they want to do research. It's not just like to become assistant professor, I am doing research, to promotions, I am doing research. Research should be your interest. That is needed. Then only such kind of research will be done. Otherwise, we will be doing research just for our purpose.
sir, is there something similar that if we feed this graphical data, then it can convert it into brain signals? And
That is now this generative AI has come. So sometimes you don't have EEG data for epilepsy. Sometimes you don't have EEG data for focal epilepsy, and you are applying machine learning. Then you need balance data. So machines they generate. But how do you authenticate? It is not people. They generate EEG signals and they say both are balanced. So machines actually they learn pattern and they give you EEG signals. That is from the they generate EEG data and people use as a balance class. Like for coronary artery disease, you have fuse data because most of the patients when they have this disease, they go to hospital they die. So we have less data. Machine learning will even less data they will learn and they will give you ECG for coronary artery disease. And then you can use normal and abnormal equal numbers. So that's balance classification. Yeah. Please.
So how you think that classical TSP method will still be relevant in future, or we should shift toward machine learning?
That is actually a very good question. And uh, when I started doing research actually in signal processing in 2003, that time many people used to work in signal processing. Signal processing was the major research area. Then slowly this machine learning came and signal processing is side. But again, I have seen now many people again they shifting to signal processing. Signal processing and machine learning both are actually fundamentally different. Machine learning means like it is one kind of data science where you have data, then you from the data you want to understand everything. For example, like ECG, electrocardiogram signal, ECG, and the ECG is generated by the heart. So I want to know each and everything about the heart from the ECG. That machine learning does. So one of the major limitations of the machine learning is not including system from which data is generated. So like I am recording ECG signal to understand the heart, but there is no heart in the machine learning. Machine learning is data dependent. So one of the major limitations of the machine learning is doesn't include system from which data is generated. Signal processing, whenever you say signal, this means system is there. So signal means it is generated by the system. So for each signal you have system, and when system you have signals. So whenever you actually use signal processing, indirectly you are actually assuming that there is a system. But in machine learning it is not. So when you do system science, system-based approach, then actually machine learning may fail. So signal processing is system-based approach, and machine learning is data-based approach. So signal processing for me it is better, and machine learning can make automated systems based on the pattern. But how to get the interpretation of the pattern, that signal processing can. Fourier work, whatever Fourier transform you have, actually very less people know what is inside of the Fourier transform. Why Fourier transform is not just like a mathematical tool. Fourier actually, it was in heat mass transfer, it was developed. And he represented heat in terms of sinusoidal functions. And heat was generated by the system. Whenever you have heat, you have something to do. Just I will give an example. It will be difficult for you to think these days. Old time, when I was a child, nearby villages, there is any celebration, any function, marriage, we used to see the smoke. If smoke is there in that village, this means we used to believe that there is some nice food is going to be prepared. And all of us from the village, without any invitation, we used to go there. Nobody used to invite. That was signals and systems. So based on the smoke, we detected there is a system. System means good food is prepared. So similarly, like Fourier, based on this heat, he represented in terms of mathematical expression, but heat was generated by the system. So wherever you have heat, there is a system. And indirectly, he represented the first time in the literature heat over the finite interval of time with the help of infinite interval of sinusoidal functions. That was the breakthrough. But this was also breakthrough that smoke, whatever heat, it was generated by the system. System is there. So the system based actually signal processing means you have actually system. Data science doesn't mean that you have system. It may be text, Facebook data, it may be LinkedIn data, it may be any other kind of data, but signal processing generally we apply for system based. So system interpretation is very, very important. If you want to know what is the disease, if it's a normal abnormal, machine learning can help. But what is the level of the disease, what is the stage of the disease, then signal processing. Signal processing can give interpretation, explanation. Machine learning just like black box. So both are needed.
Disease monitoring for agriculture purposes, and what is the variety of that?
Slowly now things are changing. We used to stay together, we used to stay in joint families. Now, nuclear families, only you will find big houses, only 1 or 2 persons are staying. Our time houses were small, many people used to stay. So now this new area of research is coming, that is what you are saying, the smart health monitoring. One person is actually, these days people are rich. You will find most of the people are rich, like investor and all this. They stay in house. One person is only one in the entire house. Now, how do you know he is alive or died? So people use a smart health monitoring. They report machine learning, vital parameters, and that person may not come back from the washroom. He fell down somewhere else. So that vital machine learning it quickly generate alarm sent to hospital. That person is actually has some problem. Come and see. Their relatives listen. So this. Similarly, agriculture also sometimes crops people do monitoring and this machine learning can help you. This is monitoring. In the initial stage, you can detect, then you can do timely treatment.
Morning, sir. So my question was about the formation of words using the EEG signals. So how you distinguish for what I think that EEG signal for similar word will be different for different people. So how do you distinguish particular words from the EEG signal?
It is actually really different, but there are some features, silent features, they are same. So for example, epilepsy, person has epilepsy, seizures. Then everybody will have different signals. Everybody has different brain. Everybody will have different signals, but in the signals you will have spikes. You will have presence of large amplitude. So that is why we go for signal processing, which can give you features. Features are same, but signals are different. So we look such kind of features which are actually similar. Have you seen Nepali person? 10 Nepalis are there, still you will detect is Nepali. How do you know? They have certain features. We have certain features. Sometimes we say a person looks like from this place. A person looks like from South Africa. Person looks like from different. So everybody has actually we have features, but still all are different. So features are common.
So the follow-up question was that when I think about a single word, I don't only think about the particular word. I have many inner thoughts about it. So like if I am thinking about creative people, I have many thoughts in the background. So how do you distinguish?
That is actually different thinking process. That is, but in when we do this processing, we are assuming that at that time we have that thinking.
No inner thoughts are mentioned.
Even whatever disease diagnosis we do, when we are doing coronary artery disease diagnosis, we are believing that you have only coronary artery disease. So multiple cases, then it is different.
So do we train the person who is using the easy signals, or do we ML distinguish particular words from the noise?
No, this is not noise. That is actually multiple thoughts are coming. So there are two ways. Generally, like this EEG rhythms I have shown you, rhythms. So there are two interpretations. Two kind of people are there. One kind of people they have one activity at a time. So that is actually time varying. So at a time you have one rhythm, other time other rhythm like that. For other person you can have all rhythms at that time. So multiple tasking. So both are actually different approaches. So like multiple tasking, then you should have multiple rhythms at a time. Single tasking, so there are many people they do focus on one activity, other activity. Many people they see many things. That is focus.
Thanks.
Dwapur Yuga time, there was no written test like today we have. So Dronacharya asked all Pandavas and the Kauravas, they come and we'll have exam today. Then Dronacharya asked Duryodhana, Duryodhana, what do you see on the tree? Duryodhana say, I can see the tree, I can see the Guruji, I can see all of my brothers, all of my relatives, all are here. Then Guruji says, you don't see anything. Then Guruji asked Arjuna, what do you see? Arjuna says, I see only eye of the God. Then Guruji said, you are the perfect person. That is focus. So this is one task. You're looking one activity. Duryodhana is looking all rhythms, all things. No, that is a poor focus. So there are two kind of people in like generally we have. One is focus on one thing. Others they are focusing on many things. You'll find they are watching television also, they are having food also, they are talking to all of many things are going on. But there are some different kind of there is only one activity. So it depends on the nature of the activity. You are doing multitasking, then you should consider all rhythms in your processing or machine learning. If you are doing single tasking, then that is completeness of the rhythms. Focus is very important.
So here you have emphasized on schizophrenia. So can we classify different types of diseases also?
Yes. So schizophrenia actually like still there is no distinguished features in the EEG. Like in other diseases like depression. Depression also is still today there is no specific features in the EEG. People are developing stage. They want to find out the features for the depression. So like depression, schizophrenia, questionnaires are important based on your behavior analysis, based on other symptoms to be diagnosed. So together with this machine learning, we also use some clinical information based on the questionnaire in the decision making systems. So we can apply these methods for depression, anxiety, stress, sleep stages, sleep disorders, all neurological disorders can be. People do that.
And so what is the duration, like in which duration we can sense?
Yeah, that is very good question. So here, this is based on the neurological. Fifteen minutes. So neurology says 15 minutes EEG signal is sufficient for this. But the signal processing has limitations. So what we have done, is we have segmented this data for some seconds. Then after that, these 15 minutes, the patients are showing symptoms. Their schizophrenia can be seen by the neurologist. Behavior that is reflected. That. And EEG signal, we settings are there, some test settings. We want to detect with as less as length. It depends on the signal processing, machine learning. But epilepsy, 5 minutes duration, it has been shown 5 to 10 minutes before you can predict. So this 5 minutes is the time which is needed to understand epilepsy. Like 2 minutes you cannot, 5 minutes before one can predict. So here, this 15 minutes is a neurologist time, but signal processing, we want to know it in terms of seconds. But this means 15 minutes, this person has that episode of the neurological disorder. So there is a channel selection actually, a channel selection criteria. So it depends on the disease. For example, epilepsy. So epilepsy, epilepsy seizure case, we see the variance of the particular channel. Variance, if it is higher, this means it is noise. So generally, epilepsy, the short term, like we say, no, this your friend is short tempered. Short tempered means for the small interval time he become angry. After that he becomes nice person. Similarly, it happens for epilepsy. Just for some time it comes, spike will come. After that it become normal. So we see this short temporal behavior. So if variance is very less, and then we consider it's like epileptic seizure. Variance is higher, this is noise. So we select one channel with the smallest variance, and other channels like 4, 5, based on the mutual information between that channel and other channels. So because other channels also should be similar to Iecs. So in that way we go for, and sometimes we see the regions also, brain regions. So this is for generalized seizures, and sometimes focal epilepsy means there is certain region that is responsible for generating the seizures. So we focus only on that region. It depends on the neurological disorder. So this brain is actually very important part in Shastras. There are many work in the world. Which work is good? So the Shastra says if you understand life, birth, death, and brain and diseases, then the best. So brain is actually machine learning. Whatever you have today, AI, ML, that came to understand the brain. 1965, 1960, people, this artificial neural network, integrated fire neurons, they came to understand the brain. But now nobody is understanding the brain. They're solving outside. Yes. Right. So the whole purpose is to understand. We still we know only 10% of the brain. In the Tri University Berlin, they have brain research center. It will look like our IT Indore campus. So the entire institute is on brain only. So brain looks like small, but it's not small. A lot of study can be done. Any other questions? So this talk was on basis functions, selection of the basis function depending on the type of signal. Similarly, nature has given us foods also. They depend on the type of the actually nature of the similarity of the parts of the body. If you want to have good brain, what we should eat? We should akhroot. Akhroot looks like brain. If you want to have good heart, what we should eat? A tomato. If you cut tomato, it looks like the heart. It has 4 chambers. If you want to have good eyes, what we should eat? Carrot. Carrot, it looks like eyes. If you want to have good kidneys that we call kidney beans. So nature also has given various foods which look like. Okay, thank you.
Thank you, Professor, for this enlightening keynote address. Your valuable insights, expertise, and thought provoking ideas have greatly enriched our understanding of the topic. I now invite our respected Dr. M. Suresh, Dean SEEE, to present a memento to Professor Ram Vilas Kajori.
Next, we are ready for our next invited talk of the morning. We are delighted to be present amongst Dr. Ambika Prasad Shah, a researcher who is shaping the future of intelligent electronics. Now, I would like to invite our professor, Dr. Rupesh Kumari, to give us a brief introduction of our invited speaker.
Yes, sir. Yeah, right here because control guns.
Dr. Saha is an associate professor in the Department of Electrical Engineering at the Indian Institute of Technology, Jammu. He received his PhD from IIT Indore and subsequently served as an postdoctoral fellow at the Institute for Microelectronics, EU, Austria, where he further strengthened his expertise in advanced microelectronics and integrated circuit design. His research interests span VLSI design, semiconductor memory technologies, low power and high performance circuit design, hardware security, fault tolerant system, reliability analysis of digital circuits, and circuits for biomedical applications. Dr. Saha has authored more than 110 research publications and 2 books, making significant contribution to the field of microelectronics and semiconductor technology. Dr. Saha's excellence has been recognized through several prestigious honors, including the Young Faculty Research Fellowship from the Ministry of Electronics and Information Technology, the Young Scientist Award from the MP Council of Science and Technology, and Best Paper Award at the VDOT conferences. He also served the research community as an associate editor for the leading IEEE journals, including IEEE Transaction on VLSI system and IEEE Transaction on dependable and secure computing. Welcome you, sir.
So good morning everyone.
Excellent. I would like to request Dr. Rupesh Kumari to come forward and present the bouquet to our respected invited speaker, Dr. Ambika Prasad Shah, as a gesture of our warm welcome.
I'm second after excellent talk by Jerry, so I don't know how much I can fulfill this one. So let's see. Because he's also expert in AI, so speaking in front of me is my professor also. Uh, I will try to speak. Let's see what I can. So basically, my talk will be related to the use of AI in semiconductor manufacturing because semiconductor is now a booming domain where we need a semiconductor chips for every applications. From biomedical to security to AI, everywhere you need chips, right? But sometimes to design a chips, you also need to use the AI so that you can get accurate chips, better yield, better performances, and more robust system you can develop if you are utilizing the artificial intelligence in the semiconductor manufacturing. So this is what my objective would be. Basically, I will be talking about how an AI in semiconductor manufacturing is transforming the chip design, because people are using chips for the AI because you have a TPU, GPUs, and all those to run your algorithms. But whatever algorithm you are running, you need a very complex chips, and those complex chip designs are also too much complex. Ultimately, if you want to increase the yield, you need to utilize the AI tools so that you can get better design, better chips, better kind of. Uh, so anyway, I'm Ambika Sasta. I came from IIT Jammu. This is one of the 23 IITs you can see at the top here. So I'm at the top of the country. One of the IITs. Okay. And yeah, it started in 2016, and yeah, this is some of the nearby good places in Jammu and Kashmir. Like this kind of scenic beauty you can see near around. Yeah, this is the panorama view of my campus. You can see very limited buildings, but yes, behind the hill you can find n number of more buildings. So we are trying to preserve the nature and just following the hills, and accordingly we are creating the new buildings. Yeah, this is about my department. Currently 25 faculty members, spanning from different domains, from VLSI to control, instrumentation, RF, and microwave, AI as well. This is what my research lab is, ICDSQ lab, where I am leading the lab. Especially, I have different kind of research domain where I am working on. That starts from the reliability to the security, quality, so all these kind of research we are doing, including biomedical IC design as well. And Professor Kasur is also one of the co-PI of our project, IPS chip, which we are trying to develop for the pacemaker chip design. Yes, this is my team, a small team. Now, because if you talk about the MAPT roadmap, MAPT roadmap simply says that any kind of need, any chip design is having certain purpose, and some purposes are that depends on three things. Need and driving forces are the sustainability and the energy efficiency. Second domain is the security and the privacy, and third one is application drivers and the system requirement. Because whatever chip you are trying to design, those chips depends on for what applications you are trying to utilize. Day by day, we keep on generating lots of data, and if those data are not secure enough, because whatever data you are generating, whether from either from mobile phone, WhatsApp, whatever your mediums you are using, you keep on generating the data, and maintaining the security of those data are equally important. So the second driving force is the privacy of yourself, your data. The second one is the sustainability and energy efficiency, how efficient chip you can design so that your battery lives and other things can be enhanced. And third and very important thing is, whatever the chips you are designing, they depends on a certain applications. For what applications you are talking about, they are really very important. And these three components decide the need and the driving forces. But if I have to achieve all these three things, which are important for the society, because they are trying to give us the prosperity, if you are trying to think about the application specific designs. If you are thinking for the sustainability and energy efficiency, definitely you are thinking for the planet and the people. And if you are talking about the security and the privacy, okay. So if you are talking about the security and the privacy, that gives us the prosperity and the planet. So these three things are, we are trying to fulfill three key requirements: people, planet, and the prosperity. And considering these three needs, you can touch at least two of these important P's in the life. But if I have a driving forces, you need certain amount of chips, and those chips can be, they could be the photonics chips, they could be the analog mixed signal, they could be the heterogeneous, different kind of packaging you need to have, different kind of processing units you need to have. So these all are the chips, SIPs, and the chiplets you need to fulfill the need, whatever you have decided based on your requirement, whether it is energy efficiency, security, or application specific. But to design those chips, you need some foundational ecosystems. And what those foundational ecosystems are? The foundational ecosystems are nothing but they are the manufacturing process. The second one is the material, substrate, and supply chain, whatever is required in the semiconductor ecosystem. And third one is design, modeling, testing, and the standards. Okay, so these three things are required. One thing is really very important here, the manufacturing process is important because we keep on manufacturing the devices. The size of transistors are less than 1 nanometer now, or 1 nanometer or 2 nanometer. And this much of complex chip design or this much of small transistor designing is required sophisticated kind of process. And AI can help us to enhance the quality, enhance the yield, better outcome, better performances. And if you look all about all these kind of circles which we have drawn here, this cannot be fulfilled without the need of manpower or workforce development. Ultimately, the big backbone behind all these activities, what we are trying to do, are nothing but they are the workforce development. Okay, so this gives us the idea. Okay, for better chip designing, you need a joint effect or joint efforts from all the domains, from manufacturing to design to packaging to materials and all other processes. So here are some glimpses that gives you the idea like why chip industries are important. You must have seen multiple articles which are available. The semiconductor shortage is mostly because yesterday in the panel discussion we were discussing Professor Bhupendra, he asked like, okay, few years back during the COVID time there was a shortage of chip, and because of that your automotive industry was delayed by at least 6 months. Okay, because of a small chip. So there are a lot of articles. It's not about the automotive industry, but it's everywhere where the requirement of chip industry is very high. If you look, the shortage of the chips are keep on increasing, and that gives us the idea. Okay, we have to keep working on the VLSI domain, chip designing, so that we can fulfill the requirement and we can fill those gaps whatever we have here, the supply chain. This is a really very important thing. Not the shortage, but maintaining the security is also very important because we keep on generating the data every day. And if we keep on generating the data, maintaining the security of those data are equally important. And now, these are some recent news. If we talk about, yes, the impact on the AI sector is also very important, very high, especially of the chip designing. Okay, so, and these are some of the recent news. Nowadays, you must have seen the memory is now in the shortage because you are not able to get the RAMs, right? That is why the cost of your entire computer is keep on increasing these days. Previously, whatever computer you can purchase with 1.5 lakhs rupees, now you need to pay at least 2.5 lakhs rupees. This is only because the cost of the memory has been increased. Okay, so this is going to be until 2027. The memory shortage is going to be there, and that is why you need to do research, especially on the memory, so that we can try to fulfill those gaps, those requirements. And if you look, the China wants the chip shortage as like one of the important concern, and war is also impacting the life. If you look, the recent news says that the Iran war choke points begin to cause double the global supply chain, especially in the chip designing. What does it mean? It simply means that semiconductor is also affected by, the chip designing industry is also affected by various activities which is happening around us, whether it is the war, whether it is the COVID or anything, they are going to impact a lot. Okay, so we have to take care how we can fulfill those gaps so that this shortage can be minimized. Considering this, we already know that the AI is a hype, right? No, it is a need. So the AI hype cycle, if you look, everywhere the AI is keep on increasing. If you look, this is the peak time where the AI is having. The AI agents, now this is the time of the AI. AI agents. AI agents are helping to facilitate your process, whether it is the semiconductor manufacturing process or any kind of analysis. AI agents are helping us, and they are at the top, which are helping in all the industries, whether they are the chip industry, biomedical industry, they are defense industry, wherever you think, everywhere the AI agents are helping us to facilitate your process, improve the quality, improve the yield. So, one thing I just wanted to tell here, I just want to show here where we are, from where we started and why there is a need of AI, especially in the chip design. If you look here, the first processor was designed in 1971, Intel 4004, okay? And the latest processor, if you look, if they utilize a 10 micrometer CMOS technology, they had only 2,300 transistors. Now, if you look the latest processor, which I'm talking about for the computer, not for the GPU and other things, I'm just talking about general purpose computer. The latest processor is the Ultra X9, which was launched its first quarter of 2026, and now they are utilizing the process 3 nanometer technology nodes they are utilizing. If you look how much advancements has been done, previously they started from a 10 micrometer and now they are at 3 nanometer, huge difference in the dimensions. How we can achieve this kind of qualities? If you look, the number of transistors are more than 17 billion transistors. Previously we had around 2,000 transistors, now we have 70 billion transistors. The size of the chip has been reduced. What does it mean? It means that you need a complex process, you need the many complex things which can help us to integrate these many transistors per unit area. This does not look that much simple. We cannot simply say that, yeah, we have just 8 or 17 billion transistors. No, they are a very large number actually. Okay. So how we can achieve all these kind of performances? These kind of performances can be achieved with the help of AI as well. So I'm trying to help you here how AI can help you in the entire supply chain or entire process from design to the fab, so that they can be utilized and you can get better yield, better performances, better outcomes. Okay, so this is nothing but this is a supply chain. Ultimately, if you are the VLSI engineer, definitely you need to start from the scratch. You need to bring some IPs. You need to use the EDA tools, and then accordingly, based on your logic, you have to use. You can develop, and accordingly, you can complete the fabless designs. Then you can send to the IDMs to fabricate it. You will use some model files from the foundries. There are different foundries, TSMC, UMC, and all those. They provide us the model card, and with the help of those, you can design your chip, and that will be nothing but they are the fabless design houses. Okay. Other than this, if you want to fabricate them, you want to package them, definitely you need certain industries like the equipment industries, raw material industry, packaging industry. So the VLSI does not only mean that if you are the designer, VLSI is done. No. VLSI has a requirement of all the domains, not only the VLSI, not only the electronics, but material guys can also contribute in your career. The chemical guys can contribute. The AI, the mathematics, everyone need to contribute so that you can get the entire supply chain from design to the packaged chip. Okay, so if you want to achieve the packaged chip, definitely the multiple things are involved. Now, the important thing is where the AI is going to help you to enhance the better chip design. They can be added into the EDAs. EDAs are nothing but you already know that, which are the cadence, synopsis, mental graphics. These all are the EDA tools. And if we have added the AI agents in the EDA, definitely they can help you to get better yield, better performances, better optimization, better placement, better routing. All these kind of process can be achieved with the help of AI. So AI is not just to use like a chat GP, just search your query and get the answer. No, AI can also help us in the semiconductor industry so that you can enhance your yield, you can enhance your proper placement in the routing as well. Okay, so these are the entire supply chain. So ultimately, they start from the EDA tool. They can be used in the modeling part. They can be utilized in selecting the proper IPs, because you have the lots of IP already available. Which IP should I should use in my design? You have to pick it randomly. If you have, let us assume 1 million IPs if you have, and if you have to select 10 IPs, it's very difficult to pick 10 IPs from 1 million IPs. So what you will use? You will apply some AI algorithm that can, based on your need, you can decide, okay, which IP I should select, and accordingly I can integrate based on my needs so that you can get better yield, better performance. So the selection of IPs, optimizing the EDA tools, EDA flow, these all can be enhanced with the help of AI agents, with the help of AI tools. So these are some of the domain where you can utilize, especially in the fabless houses. I'm not just talking about the fab houses. I will discuss later on how the fab houses are utilizing a different process so that they can enhance their yield, especially at the time of fabrication of the chips. At the same time, it is really very important because the designers need to design the chip. They need to design based on the specifications given. Okay. For example, if I am the user and I need certain chips, what I will do? I will tell, okay, my application is this one. These are the specifications, and I will ask the chip vendor because I cannot design my chip and I cannot fabricate it. I cannot package it. I will ask someone who can provide the chip, whatever I need. Okay. Based on that, what I will tell, I will ask the chip vendor to provide a chip. What they will do, the chip vendor will contact the IP vendors because for any applications, what kind of IP need to be integrated, they know it. Okay, because they know the specifications. Based on that, they will pick the IPs. So they will ask the IP vendors, and IP vendor will give you the IPs back. But that IP must be trusted. I told you the security and the privacy is really very important. The security of data is important. From where security starts. Security does not only mean with the cyber security. It's not just network security. But security also means that whatever hardware you are trying to utilize for your system, they should be secure enough as well. If your hardware is not secure, whatever the communication we are doing over here, if these communication devices, electronic devices are not secure enough, I cannot guarantee my network is secure. So the hardware security is equally important. That is why you need to validate whether IP vendor is giving you the trusted IP or not. If they are giving the trusted IP, I will share this trusted IP to the design houses, design teams, and then they will start designing from the RTL to the GDS, and they can complete all these things. They can get up to the layout. Once the layout is done, this is what is being done at the design houses, at the fabless design houses. Now, once I got my GDS, this GDS need to be sent to the fab houses, foundries. Okay, so again, this particular design will be sent back. The designer team will send back the design to the chip vendor. Now, chip vendor will contact the foundry who will fabricate the chip. They will convert their layout into the wafer and they will fabricate it, package it, and again the packaged chip will be sent back to the chip vendor, and the chip vendor can give you the trusted chip. So what does it mean? It simply means that the trust and security concern can be at any point. It can be at the IP vendor provider. It can be the design houses. Because if I am a designer and if I am not trustworthy, what does it mean? I can add a Trojan inside it. That Trojan can be activated at any conditions. And if this is happening, this is the problem, especially because if you are trying to utilize those chips for the defense application, and if they are triggering at particular conditions, which the tester cannot test it, that's the problem. Okay, so the trusted IPs, trusted design houses, trusted foundries, trusted team is really very important, so that you can enhance the trustworthiness and you can get the authentic chip and you can maintain the security of those hardwares. So that is really very interesting part. Once we are ready with this one, now I will say, if I have to design a chip, what is the simple process that we have to do? If I have to process this, definitely you already know that because most of you are master students, LSI master students, you may be knowing because the silica, because the basic substrate that we are using these days are the silicon. And the silica is the great source for the silicon. So if we can get some silica, definitely after refining it, we can get the wafer or ingot. You already know the process how to get it. Okay. The next process is the getting ingot. Get the wafer slices, do the slicing, get the wafers, do the patterning. This is what the wafer looks like. And these wafers are nothing but after processing, you will get this shiny part. And these all are nothing but they are the small chips. Now, because in a single wafer, you can have multiple chips. You need to slice them. You need to get it out a single chip. So you will get, you can slice like, you can dice like this one, and then you can get a single chip from a single wafer, something like this one. So in a single wafer, you can have multiple chips. And once you are ready with this kind of dice, or this die you got it, Now what you need to do? You need to do the wire bonding, and then you need to package them, and ultimately you can get the final product something like this one. I explained the entire process in just in 20 seconds, but it's not a 20-second job. Okay, it required a complex process. From refining the sand to get the 100%, 99.9 times pure silicon is really very difficult to get it. You have to get the ingot, you have to get the proper wafer, you have to proper process it so that you can get the better yield in a single wafer. Your edges should not be having more process variability. They should have also the better yield. This is what is the need. At the time of dicing, probably some of the dice can be broken down. This is also one of the problems. So if somehow we are trying to utilize the AI to detect where the problem is, where the yield is reducing, we can enhance those things. So AI can help in process as well when we are trying to process the wafer fabrications. Okay, so now I will talk about, yeah, this is nothing but because the trust is important only because at one place you cannot do everything. You need multiple parties who can provide the IPs, who can do the designing, fabrication can be done at other places, packaging will be done at other places. So all the parties should be authentic, they should be trusted, only then you can maintain the security in the authenticity. One very interesting thing is, if you talk about the evaluation of the VLSI industry, they started from the 1990s or 1980s. At that time, the size of the transistors was 1 to 2 micrometer, which is very large device. They are very long channel devices. At that time, the major concern that we have was the functionality. If we are able to get proper functional design, that was perfectly fine. There was no further consideration because whatever you are trying to connect the devices, you are getting the function. If you are getting the function, it is fine. But with the advancement of the semiconductor technologies, the next kind of evaluation in the submicron technologies, there was not only the functional testing, but at the same time, the timing validation is also important. Now the timing becomes one of the factors that came like, okay, my design is working perfectly fine, like the functionality it is perfectly fine, but how much time it is taking to give the output, that matters a lot. How quickly I can get the decision. So timing information become another challenge that need to be optimized. So the second challenge in the submicron eras, the other than the functionality, the timing becomes another driving force, another parameter, another things that need to be optimized. But the problem does not stop here. The problem again further increases if you talk about the deep submicron technologies. In the deep submicron technologies, the functionality and the power, the timing was a concern, but now the power became one of the major parameters that aided, like how optimum power, how you can optimize the power so that you can use your design for the low power applications. So the functionality, timing, and the power becomes the third component that becomes like one of the important consideration so that you can enhance the battery life, you can reduce the power consumption of the chip. And that becomes the third component. But the challenge does not stop here. In the next evaluation in the semiconductor industry, if you talk about the nanometric SOCs, the functionality, timing, power, and then the fourth component has been added, and that is the reliability. Because with the time, we keep on miniaturizing the devices, the size of the transistors are keep on reducing, and getting better reliability is becoming one of the challenges. So maintaining the reliability, how reliable systems you can develop, that becomes the challenge. So the next component, next kind of challenge in the nanometric era was the functionality, timing, power, and the reliability. Is challenge stops here? No. The further challenges came if you talk about the next era where the thermal stability becomes one of the challenges because the devices are close to each other. If the devices are close to each other, they are creating the hot spot, and one part of the chip can become very hot and might be functionality cannot be whatever we are trying to achieve here. So the thermal issues becomes one of the serious concern. Other than this, the electromagnetic interference becomes one of the concern because the transistors are very close to each other. If they are very close to each other, interference may happen, especially at the high frequencies. So you have to eliminate those as well. So the EMI and the thermal issues are one of the concerns that need to be addressed. But again, the challenge does not stop here. One more challenge came, and that challenge is how much mechanically strength you have. So it does not mean we have solved all the problems and no further problems will come. No, definitely the problem will come. Because the next generation or next technology is the 3D ICs. We are trying to stack the device on top of it. And if we are trying to make a 3D ICs, integrating those 3D ICs becomes one of the challenges. So that will become another challenge in the near future. Other than these things, off track, the security of the data, whatever the device or whatever the process I am trying to follow, how secure they are also one of the bigger challenges. So it simply means that with the evaluation, we cannot simply say that, okay, the challenges has been done, now we are trying to get the output. No, the new challenge will keep on coming. Okay, and we have to solve those problems as well. And that's really the interesting part. देखो दूसरा नहीं है कल से टूट रहा है कल तो बदल रहा है okay so this is what I just talked about. What are the different design complexities, design challenges, but the question is still open, like how AI can help in the semiconductor manufacturing process. Let us try to understand those things as well. How AI can help in the VLSI, because nowadays generally there is a myth like VLSI, the AI is going to kill everyone, but this is not true actually. If you are a good user of AI, definitely you can enhance the yield, enhance the quality of your AI, your VLSI as well. Let us try to see how it is going to happen. If we talk about the chip designing challenges, if you see the chip design challenges, there are certain challenges. The first challenge is the advanced node transitions, because if you look, every year the new kind of technologies are coming up, new nodes are coming up. So if I want to set up a fab house, if I have set up that for a particular technology, then I have invested a lot. And if I have invested, and next year if technology changes, I need to change many things. And that becomes one of the biggest challenge, because the equipment need to be changed, many things need to be changed, and that require huge investment. So the first one is the advanced node transitions are keep on happening every year, and matching with those technologies are really a big challenge. The second one is, because shifting from advanced node is required significant design changes. The second one is the AI and HPC demand. Every day now we need the lots of chips are required these days, especially for AI applications or for big servers. So, and for these things, you need to have a good designer, and that is also one of the complex design process is. The third challenge is because nowadays lots of companies are keep on claiming like, okay, I am going to design this one, and you are going to design this one. If you have disclosed one thing, your market is gone then. So there's a huge competition is going on. Rising competitions also gives you the challenge to match with the market. It's not like just whatever you are doing, just keep doing that and you will get the things. No, you have to follow the market and accordingly you have to process it, and that becomes one of the challenge.
Yeah, I think it was given more.
Okay, so this is a rise in competition, and then investment risk, because if you have invested a lot in advancing the technology, next year it will be upgraded, and then your money is gone. So you have to take a lot of risk, and then there are ecosystem complexity, because the things are keep on increasing, the complexities are keep on increasing, and that becomes one of the challenge, especially in the chip design. Now, if we talk about how the AI can help us to get better yield, if you look the traditional design cycle, if you are a designer, if you are trying to get a chip, that typically requires 10 to 12 months if you are trying to follow the typical process to design the chip. If you are taking the transistors, connecting them, doing the simulations, doing the synthesis, layout, and everything, whatever you are trying to do that, in all process, you need at least 10 to 12 months so that you can generate your GDS. But the AI can help here. How? The AI, if you are trying to use the AI augmented design cycle, definitely this kind of design cycle can reduce your entire life cycle from 10 to 12 months to 3 to 4 weeks. And this is what the importance of the AI is. Okay, this is going to help you. And if you see, the chip design accounts for over 53% of semiconductor industry expenses. And if you are trying to utilize the AIs, definitely they are going to help you to reduce the cost as well. And that is really very important. Okay, so that is the AI can help us to for the collaboration tools. They are trying to get the cost optimization can be done. The accelerated development can be done with the help of AI. You can accelerate your process and you can design your chip with the less time. And then you can have the efficiency can be enhanced because the automated proper placement, routing that can be done. And that can help us to get better efficiency. And then at the end, you can get the enhanced innovation because you're trying to utilize the AI agents to optimize the process from the RTA to complete GGS flow. So this is how the AI is going to impact your design cycle. The traditional time that required 10 to 12 months, then if you are trying to use it, the AI can help you to build your chip in 3 to 4 weeks if you are a very good designer. So this is what the advancement of or the use of AI can help us to get better chip design process, and these are some of the advantages of those things. Similarly, if you talk about, because if I'm just following the traditional design, in the traditional design, I have to do many things like a manual. They are time consuming. There are high chance the error will be there. But if you have used the generative AI to design the chips, definitely this generative AI can help us to automate the IP search. I just told you, because you have millions of IPs, and out of those millions of IP, you have to pick a best one. How to pick that? Because millions of IP, you cannot search one by one. You cannot go one by one. You have to automate them so that the best IP you can pick and you can utilize in your design. So the proper automatic IP search, the faster development, this can be done with the help of generative AI. So here the AI is helping in the VLSI industries, especially in the chip design process. Similarly, if you talk about if you have the AI powered tools, the EDA tools, if they are AI enabled, I already told you they can help you to proper placement, proper routing, proper selection of the IPs, proper interconnections, proper optimization. This all can be done with the help of the AI enabled EDA tools. So the AIs are helping, especially in the faster development, like the floor planning, routing, error analysis. All this can be done quickly with the help of AI, and this is what the importance is. And at the end, if you have the AI-driven designs, definitely better innovative ideas, innovative designs you can have, efficient design you can have. You can have the accelerated development. It will require the less time to development. I already told you the design cycle can be reduced from 10 months to 3 months, 10 months to 3 months or so, even less than that. These are the advantages of the AI, especially in the VLSI process flow. Now, if you talk about how the AI can help, especially in the EDA flow, okay? In the EDA flow, if your EDA is AI enabled, definitely you can have the better design exploration that is possible. The RTL design optimization can be done very well because you have the RTL, but whether they are the optimum design or not, this can be done, they can be optimized with the help of AI. So if your EDA tool is AI enabled, definitely that can help to optimize your RTL as well. The physical design automation can also be done because whatever the layout you are trying to design, if you are using the AI, proper automation can be done, optimum layout you can design, proper placement can be done. So this is what the importance of the physical design automation as well. Similarly, you can do the runtime design rule check, whether whatever the connections you are making, whatever the RTL you are writing, you have to keep doing all these design rule checks, whether they are following those design rules or not, and they can also be automated through the AI. And this is what the importance is. The automated test pattern generation, because once you have designed your chip, you want to test it, functionality test you have to do. And for that, what you need to do, automatic test you can then generate, random test you can generate, and you can validate your design whether they are properly working or not. And this is how the AI can also help especially in the pattern generation and the testing. And at the end, the design for manufacturing and the design closure. So if your EDA is AI enabled, this will enhance the quality and this will speed up the process. With the less time, you can get better yield if the AI enabled EDA tool if you are trying to use it. Okay. So this is what about the AI enabled EDA tools are. On the other hand, if you talk about the chip design process cycle, in this chip design process cycle, they are nothing but the initial chip designing, the iterative refinement can be done with the help of AI, optimization and testing can be done on the refinement at the refinement side. The verification, at the verification stage, you can use the AI. Okay. Similarly, the error log management, because whatever the error you have, you just check it, analyze it, and see where the problem is. And this can also be done with the help of AI agents. Okay. And then IP representative management, I already told you, picking a best IP is important. Because if you have millions of IPs, and out of those millions IP, if you need a 10 best IPs, you have to use. You cannot simply pick and connect. You will not get the best IPs. And for that, you need to use the algorithms, AI algorithm. Based on your need, a best IP will be picked, and accordingly, it can be utilized in your design. Okay, and then the distributed team, because many people can be collaborate and they can work, that will reduce the design cycle and the delay will be reduced. So this is what the advancement or the AI integration in the EDA tools are going to help you to enhance the yield, reduce the design cycle, and getting better outcomes. So now once you have done, you got the GDS file generated. Now this GDS is really very important. This GDS is being sent to the fab houses for the fabrication. How much time do I have? Right. So if you have a GDS to generate it, like this can be done at any of the academic institutions. Now this GDS is being sent to the fab houses for the fabrications. Now the real challenge starts here actually. You got the GDS, now you want to fabricate this, convert this GDS into your actual silicon chip. Okay, and for that, what kind of process you have to adopt? There are certain processes that you have to adopt, and certain processes like if you have a GDS tool that you have got from a designer, now what you need to do? There are certain processes. What those processes are? The process one is the mask preparation. You have to prepare the mask based on your GDS, based on your design. Now the question is, if I have to prepare a mask to get my design fabrication, how the AI can help in the mask preparation here? The AI can also help in the mask preparation because see, here you have created the mask so that you can get the fabrication, you can get your chip fabricated and you can get your wafer proper wafer one. But there are some optimized optical proximity correctors, they can be done. The defect detection can also be done with the help of AI. So at the time of mask preparation, you can utilize AI to optimize the optical proximity correctors. You can optimize you can detect the defects, you can correct those defects, and this is what can be done at the mask preparation. So this is how the AI can help there. The second step, if we talk about the wafer fabrications, at this stage, basically there are two things which are very important. You can control the process with the help of AI. Okay, you can optimize the lithography process. This process can be optimized with the help of AI, because ultimately you have to get the proper chip fabrication. You want a fabricated wafer here. Okay. Similarly, the third step is the wafer testing. Once your wafer is fabricated, you need to test it. So here you need to test whether there are certain defects or not. There are certain what is the yield, how much is the failure. This all can be analyzed with the help of AI. Okay. And then the next step is the dicing. Dicing is nothing but cutting down and getting one single chip out of it. Okay. And in the dicing process, there must be some micro leakage, micro defects as well. And those micro defects can also be detected with the help of the AI. So this defect cracks, monitoring the blades, how they are moving, how they are cutting, how much pieces you need, these all can be monitored with the help of AI process. And then packaging can also be done. Packaging is one of the process where you need to package after dicing it, and here AI can help, like to inspect the bonding, proper bonding, detecting the defects, these all can be done. And at the end, you will get the final chip, and this final chip can also be tested with the automatic test generation. Those kind of test patterns can be applied, and then accordingly you can get your final chips, and those can be tested here. So ultimately, what I just tried to say, like the AI can be used in the fabless as well as at the fabrication side. At both the places, AI can play a major role. If you have AI-enabled EDA tools, they can help you to optimize your design, proper placement, proper routing. These all can be done with the help of AI. Once your GDS is ready, and if you have sent it for the fabrications, there are multiple steps which involve from the GDS to getting the package chip. And at each step, AI can help you to detect the defects, to enhance the yield, to predict the proper alignment, and by utilizing these things, you can get better yield, better outcomes, more number of chips you can get per wafer. And this is what the importance of the AI is. And with this, I just want to close my session. If you have further questions, you can ask. Thank you so much.
Hello, good morning, sir. I'm Dr. Pallavi from IEEE. So we are working in the area of VLSI, like Ankur sir, me, and we are working. So I have done my research in high-level synthesis, that is starting from the behavioral specification and then coming to RTL. So I just wanted to know what are the different AI algorithms that are going in recent trends, which we can apply at the different abstraction levels of VLSI, and how do we map the parameters to different mapping, like yield power or area, thermal stability, whatever.
So it depends, like at what kind of what parameter you are trying to optimize. So there are one thing, like if you want to optimize your proper placement, so for that you need to have certain algorithm that can help to get the design, identify the proper location, proper placement, so that the delay can be reduced, metal layers can be minimized, the interconnect length can be minimized. So this is one of the thing. Second thing, if you want to detect the Trojan, let us assume some Trojan has been inserted, so you want to inspect those things, then you need to have a different kind of algorithm. I think I do not have that slide. Maybe I can say later on. So there are multiple algorithms at different stages. It's not like a single algorithm will work for all the requirements. Placement, routing, inspections, and then optimization, like power optimization, delay optimization, all this can be done with the help of different kind of tools, because they have a different kind of constraints. And if you have a different constraint, definitely you need a different kind of inputs, and accordingly it need to be optimized accordingly. So you cannot simply say like a single tool will help to optimize the entire process, but no, you need to have a dedicated tool which can solve a particular problem.
Thank you, sir. Following that, I have one more question. Like we have worked with the standard, synopsis, cadence, Xilinx, Vivado, and all of that, along with the Spartan boards and PJ boards. So now, what are the recent AI tools? Now you mentioned about AI tools based, which are helping in the entire flow. So what are the AI tools?
Okay, right.
EDA tools. Can you name some so that we can use
I
it?
think some in EDA at the placement in the routing they have added some. Actually, the names are complex. I don't know the name. I can search and I can tell
Yes,
you.
yes.
Okay, so these tools are helping us to optimize the things actually, and they have been enabled inside the EDA itself. You do not need to have like you need to add another tool. The EDA vendors have already done all this job. They have added all these things so that you can automate the things. You can optimize them.
Okay, sir. Anybody else? Any question?
Good morning, sir.
Yeah.
Sir, actually, I wanted to, you told in starting that memory, RAM memory problem is a very big thing right now. So, sir, when I was studying about how AI works and how we take data from chip to, then we took it to RAM and then we again take it back to chip. So, sir, can we design on chip memory on chip memory in a chip? So small packets of data don't need to travel to device RAM, and small problems can be solved there only.
Yes, so this is the architecture kind of concern
Yes.
you are talking about. So generally, the general purpose is nothing but where you have a separate module for the memory, you have a separate module for the controller. They are fetching the data from memory, they are executing it, again they are sending back to the memory. So they have a certain challenge because the latency is high here, the memory bottleneck is here. So to overcome this problem, there are two possible solutions. The one solution is you keep your memory closer to the processor. This kind of technology, we call it the near memory computing. Okay. But if you want to further enhance it, in-memory computing is the new paradigm where the people are working on. They are trying to execute the operation within the memory, and they are executing there only, and they are storing the data in the memory only. So the in-memory computing could be one of the domain which can solve this kind of problem. But the major problem with the memory computing could be like you need a large data to compute, and for that memory requirement will be very high, so cost is also going to be very high. So there is always a trade-off. Of course, the in-memory computing can solve this problem, this memory bottleneck problem, whatever you are talking about, but that enhance that require more cost. Also, use lots of data you are trying to transfer, fetch, execute. Memory requirement will also be increased. Then I hope you got an answer. Any other questions? Yes, please.
Hello, sir. Thanks for such a nice talk. Then, my question now, we already work over the device to circuit application. We have the equivalent memory circuit and all. But only in continuation, the madam doubts, we would like to implement the AI flavors also, right? So for that, shall we have to help get another tool or what?
Tool in designing you're talking about?
Circuit design.
No, so EDA tools they have already included, so you do not need to include the AI tools there. Where AI can be used, let me tell you. AI, so for example, especially if you want to proper, I already answered the same thing. Placement, routing, these all will require good AI agents which can help us to optimize the problem. and they are already been included inside the EDA tools. You do not need to add the additional EDA tools to optimize all this. And they are already doing all this automation.
Like Cadence we are using.
Yeah, in all EDA tools now, all the EDA vendors, they have added the AI agents that are facilitating your process. Enhancing
Suppose we have a SRAM circuit, consists of CMOS transistors. Now we have to incorporate some AI.
No, at the RTL you can do that, but schematic it's a bit difficult because schematic you are plug and play, you are trying to do that, and that's a bit difficult. But if you are writing RTL script, definitely they can. You have the delay constants, you have the power constants, and you know that you have given the constant. What does it mean? Maximum power can be this one, maximum delay can be this one, and based on that, in background AI algorithm will work, and accordingly they will optimize your RTL so that you can fulfill those constants. So, but at the schematic, it may be a bit difficult at this stage.
So we can say RTL to GDS.
Yeah, in the digital flow, it's more useful than the schematic one.
Yeah, that is more right. Okay, thank you, sir. Please.
Thank you, Professor, so for your enlightened discussions on this chip processing. So I'm basically coming from computer science area. I would like to know particularly, can we use AI in the security aspects of this chip design?
Yes.
Or is there any
I was supposed to
development?
talk about that one. So nowadays, so let us assume we talk about the security primitives. For example, one of the important security primitive is the physically unclonable functions. Nowadays, we claim that these are the biometric of a chip, and they cannot be cloned. But and how they work actually? They work on the process variability. So at the time of fabrications, you cannot get whatever you are trying to you have whatever design you have. There must be a variability. This variability is a problem, especially in terms of the reliability. But when it comes to the security, the same variability becomes the benefit. Okay, so those process variabilities are being utilized to capture the CRP, challenge response pair for the puff, and they are treating like a biometric of a chip. Now, once you got the biometric of a chip, you are seeing like, okay, for each chip you will have a different biometric, different kind of unique responses. But if somehow I know, like attacker knows, some of the challenge response pair, with the help of AI, they can predict what could be the next CRP. And if it is the AI resilient, like model attack, machine learning model attack resilient, then it is good design, otherwise it is not. So generally now, in security perspective, now people are trying to include some of the flavor of AI, how machine learning can be utilized to predict the keys.
Okay, fine.
Okay. So if somehow they can confuse the attacker, they are succeeding in the maintaining the security. But if they are able to crack it, you have to add more things to enhance it. So this is how it is.
Yeah, thank you, sir. Thank you very much.
Any other doubt?
Thank you, sir.
Thank you for the nice talk.
Sorry,
It is on AI for like VLSI.
Yes.
But sometimes we need VLSI also for AI.
Yes. Yes.
So at this point of time, there are two paradigms
Yes.
of machine learning. In one paradigm, what we do, we use conventional machine learning algorithms, and we extract set of features, then we perform training and testing and do classification, like the support vector machine, random forest classifier, artificial neural network, etc. Other kind of paradigm, we don't extract set of features, and classification process itself extract features like deep learning, CNN, all these things, advanced machine learning. So now, the first one gives good interpretability, whatever we are doing, features are there, you have good explanation. In other one, you do like classification, then you don't have insight of the process. So now, whatever the madam was asking question, which AI framework is suitable for the optimization problems for VLSI? So now there are two frameworks. So which one is useful? Like every framework has an advantage and disadvantage.
Yeah, there is always
so I
trade-off.
want to know
Yes.
like whether we should use deep learning, CNN, or conventional machine learning.
It depends on how many data sets we have, and that decides like which kind of training we have to do. One very interesting thing here is I just explained how AI can help to build better chips, right? On other way, if I talk about, so let us assume if I have to run some AI algorithm based on my data sets, based on the complexity, based on how many layers we have, how much is the complexity. That accordingly, you need a complex system who can run those algorithms. Now, in one direction, I'm saying AI can help to build a better chips. But on other hand, if I need to use the AI algorithm, if I run, I need to run the AI algorithm, I need a complex computing units. Okay, so basically, like TPUs, all these are helping us to build complex algorithms so that you can run those algorithms and they are going to quickly get the decisions. So the AI is AI for VLSI and the VLSI for AI is really very important, and there is an overlap person over here. Now, about the what kind of specs will be sufficient enough to run a particular, it depends on the data set, in my opinion, because you are expert, so you can tell like okay.
Suppose you are doing artificial neural network. We don't know how many layers are required, how many neurons are required, which activation function is useful. Like support vector machine, which kernel is useful. So that itself will have a lot of optimization has to be done to find out the good AI tool for VLSI.
Yes, yes.
So the way you are looking VLSI, similarly AI is also superior.
Yes.
Then only
so inside AI also there is a multiple unknown things, and that need to be optimized so that you can quickly get a particular.
We are assuming that we are perfect AI tool and so this is application. But AI itself has so many challenges like VLSI.
So yes, yes. More variables will have more complexity, more optimization required. Of course, I do agree with this. Indeed.
Thank you, Dr. Shah, for graciously accepting our invitation and being with us today. Your presence has truly added value to this event. I now invite our respected Dr. Punkundran, Executive Dean, to felicitate Dr. Ambika Prasad. Continuing our journey of learning, we are honored to introduce our next plenary speaker, Dr. Santosh Reddy, all the way from Aubrey, Texas, USA. I would like to invite Dr. Arindam Datta on the stage to introduce our plenary speaker who brings us the wealth of international perspective.
A senior member of IEEE, Mr. Santosh Reddy Basireddy, is a senior technology architect, enterprise system strategist, and applied AI researcher with over a decade of experience designing and delivering large-scale technology solutions across regulated industries. His expertise spans enterprise architecture, cloud computing, distributed systems, Salesforce architecture, intelligent automation, and AI-enabled enterprise solutions. His research interests include generative AI, large language models, AI governance, enterprise risk management, and the responsible adoption of artificial intelligence within complex organizational environments. He is particularly interested in bridging the gap between emerging AI research and practical enterprise implementation with a focus on scalable, trustworthy, and business-aligned AI systems. Mr. Basireddy actively contributes to the global research and professional community through scholarly publications, peer review activities, conference presentations, technical mentoring, and professional service. As an IEEE senior member, he remains committed to advancing innovation and knowledge sharing at the intersection of enterprise systems and artificial intelligence.
Here, due to unavoidable professional commitments, our esteemed speaker is unable to join us in person today. However, despite the constraints of his schedule, he has graciously recorded a special video for this conference. We are truly grateful for his time and support. May I now request the technical team to kindly play the recorded message.
Good morning, good evening, everyone. First of all, I'd like to thank the IEEE IECS 2026 Organizing Committee for inviting me to speak today. It is a privilege to be part of the inaugural IEEE IECS conference. I am Santosh Reddy Basireddy. My background is in enterprise architecture, where I have spent many years designing enterprise applications, distributing systems, and governance-driven platforms. Over the last few years, my work has increasingly focused on enterprise AI governance, and large language models. One question I hear quite often from organizations is, we have successfully built an AI prototype. The next challenge is, how do we make it something the business can trust, govern, and scale? That's exactly the question I'd like to explore with you today. Over the next 35 to 40 minutes, I'll share practical lessons from enterprise architecture, AI governance, and real-world AI adoption. My goal isn't to introduce another AI framework. Instead, I'd like to discuss why so many promising AI initiatives never move beyond the pilot stage, and what organizations can do differently to successfully deploy AI at enterprise scale. Here is the roadmap for today's session. We'll begin by looking at why so many AI initiatives successfully demonstrate value as prototypes but struggle to become enterprise scale solutions. From there, I'll introduce a practical framework that organizes 5 key areas organizations should consider when adopting enterprise AI. We'll then explore each of these 5 pillars in more detail, following by an enterprise AI reference, architecture, and the life cycle needed to operate AI system responsibly. Finally, I'll share a few practical lessons discussing where enterprise AI is heading with agentic AI, and conclude with the key message I'd like you to take away from today's session. Enterprise AI. Let's spend a minute looking at how we arrived here. AI certainly it didn't begin with ChatGPT. It's the result of decades of progress. We started with traditional rule-based systems, where software followed predefined rules. Then came machine learning, allowing systems to learn from data rather than relying only on programmed logic. Deep learning significantly expanded what AI could accomplish, particularly in areas such as computer vision, speech recognition, and natural language processing. More recently, generative AI changed the way people interact with AI by making it accessible through natural language. Today, we entered the next stage, enterprise AI. The focus is no longer just generating text or answering questions. It's about integrating AI into enterprise applications, business process, and day-to-day decision making. What's different this time is the speed of innovation. 8 years ago, building an AI prototype could take months. Today, with foundation models, cloud platforms, and AI services, it's possible to build a working proof of concept in a matter of hours or even minutes. But one thing hasn't changed nearly as quickly. Turning that prototype into something an entire organization can trust, govern, operate, and scale. That remains a significant challenge. The AI model is no longer the biggest bottleneck. Enterprise readiness is. And that's exactly where I'd like to focus for the rest of today's talk. Think about your own organization for a moment. Today, almost every organization is experimenting with
generative AI in some form. But how many have successfully deployed AI across the enterprise with the necessary governance, security, and operational controls? In reality, not many. The gap is really the focus of our today's talk. Various industries report suggest that more than 70% of enterprise AI initiatives struggle to move beyond the pilot stage. While the exact percentage varies across studies, the overall pattern is remarkably consistent across industry reports and enterprise AI discussions. These projects doesn't necessarily fail. Instead, they often become stuck. The prototype works, stakeholders are impressed, and everyone agrees their value. But when it comes to deploying the solution across the enterprise, progress slows dramatically. So what changes? Interestingly, the biggest challenge usually isn't the AI model itself. The real challenge is that organizations began asking questions that hadn't fully considered during the prototype phase. How do we govern the system? Who owns it? How do we monitor it? How do we securely enterprise data? How do we ensure regulatory compliance? Governance, security, legal, and compliance often becomes involved only after the prototype has already been built. At that stage, there is no longer evaluating an idea. They are evaluating something people already want to use. That's a much more difficult position for any organization. Enterprise AI doesn't become difficult because the model stops improving. It becomes difficult because the organizations now has to trust, govern, and operate that AI system at scale. Every AI initiative I've seen follows roughly the same path. Experiment, prototype, pilot, department-wide, enterprise-wide, and for a few systems, mission critical. Almost everyone gets to pilot. That part's usually straightforward because the stakes are still low. One team, a handful of users, nothing catastrophic if it's a little rough. Very few get past that point. It's not that the technology gets harder to run at scale. Cloud infrastructure already solved that years ago. It's just the requirement changes at each stage. A tool one team uses just needs support. A tool the whole company depends on needs governance, an audit trail, and a named owner who is still accountable 2 years later. This is really a trust curve more than a technology curve. At each stage, you're asking a wider group of people, more users, more executives, eventually regulators, to trust the same system a bit more than the last group did. Technology is rarely what's holding organizations back. It's the governance. Let's look at the reasons AI projects actually struggle. Because simply saying governance matters doesn't explain why. Through industry experience and enterprise AI discussions, a few common patterns appear repeatedly. The first is poor data. If the underlying data is inconsistent, incomplete, or poorly governed, even the most advanced AI models will produce unreliable results. In fact, generative AI is very good at making incorrect information sound convincing, which makes poor data one of the biggest risks. The second is unclear ownership. One simple question organizations often struggle to answer is who actually owns the AI systems? If ownership isn't clearly defined, accountability becomes unclear and governance quickly becomes difficult. The third is weak executive sponsorship. AI projects are sometimes funded because AI is exciting rather than because they solve a clearly defined business problem. When priorities change or budget becomes tighter, these projects often lose momentum. The fourth is security and compliance. Security, privacy, and legal reviews are sometimes introduced late in the project, after the prototype has already demonstrated value. Addressing those concerns at the end is usually far more difficult than considering them from the beginning. Finally, many organizations underestimate the importance of continuous monitoring. An AI system shouldn't be treated as a deploy once and forget application. Models evolve, enterprise data changes, user behavior changes, and regulations continue to evolve. Without ongoing monitoring and governance, even a successful deployment can gradually become less reliable over time. What's interesting is that none of these challenges are
कहाँ क्या हो रहा है क्या हो रहा है जो ब्लिंकिंग हो रहा है अच्छा ये लगाने को बोला
Another one HDMI.
सर
Another HDMI.
it's only one only for the projector.
So what was the issue?
So the issue is the cable is broken, so it's again and again blinking. So it's there, it's going under wall and up to projector. Vishnu sir came yesterday. He said that he needed
Box power supply available.
yes sir. Sir,
How it is broken.
sir here. Give me.
के बाद 5 बजे वैलिडिटी
क्यों जाना है भाई 3 घंटा क्या करेंगे
3 घंटा खाएगा भाई 5 बजे है वैलिडिटी
मैं तो यहाँ बैठ के सिग्नलिंग सिस्टम पढ़ूंगा भाई अर्जुन सर ने असाइनमेंट डाला है मैं यहाँ पे अर्जुन सर को अभी आएंगे ना मैं सर
कुछ नहीं बोला मेरे बहन ऐसे ही बता दे सनत किसका कॉल
सनत झूठ नहीं बोलते लाइक करना है
लाइक